Thank you very much, Peter. Now the floor is yours.
Thank you. Today we'll be talking about a fairly new technology in desalination called capacitive deionization. It's been around for about 5 to 10 years in its current form. It's a low energy technology and it's based on an electrochemical methodology. So I'll show you one of our small scale systems that we use for agriculture. I'll also present some detailed economic modelling of that system under a number of different situations. So MinCarb is based in Sydney, Australia. So at the bottom there you can see our factory facility and production line. We have a number of projects. We have projects in Australia focused on irrigation. In Vietnam, we're looking at addressing issues with seawater intrusion because of sea level rise. And in India, our focus is more on drinking water. So just an overview of the technology. In the top here, we have how the technology works. It is comprised of a stack of electrodes. It has a number of components, mainly the carbon layer. This is where the salt is absorbed. So when you pass a salty water through the middle between the two electrodes, the positive and negative ions are attracted into the carbon layer and exiting is desalinated water. We only require very little voltage to drive this process. So when we do, we apply typically less than 1.5 volts. And so that makes it ideal for photovoltaics. It's very easy to drive. So just quickly, I'll show you what that stack looks like. So it's many repeating layers, as you see there. The black one being the one that absorbs the salt. Now, when we make electrodes, we typically have thousands of those layers repeating and stacked up quite high. So you'll see a full electrode in another image. Just in this other slide here, or not slide, image, is the energy requirement to drive the process. Because it's electrochemical, one of the benefits is you could fractionally remove salt. So if you started with 4 grams per litre, you would only need 1 kilowatt hour to process a cubic metre. If you were starting at 2 grams per litre, you'd only need 0.5. So you can pretty much dial in the end quality that you desire. So you have a lot of flexibility in how you drive the process. Another benefit of this technology is that you can recover the energy from the process. So when you absorb salt into the carbon layer, energy is stored during that process. And to release it, to release the salt, you reverse the voltage, you push the salt off, but at the same time, you can actually collect energy during that step. In fact, we can get about 60% of the energy back, which we can use in the next cycle of the process. So this is one of our small desalination systems here outside our factory in Sydney. It is fairly small. There's my car there, so you can get an idea of how big it is. We have 1,000 watts of panel here to drive the process, and this unit can do about 1,000 litres an hour. On the inside, we have the large electrode that I was talking about. That is approximately 0.5 metres in height, and it comprised of many of those layers that I talked about. There are a number of other bits that go in there, a little bit of pre-filtration and a little bit of post-treatment, but there's really not much inside there. On the other side of the cabinet, we have the electrical components. So this is the block diagram for this system. We have a charge controller, We have a battery bank, about 300 amp hours for this system. We drive the pumps and all the other controllers from a 24-volt rail, and we need a step-down converter to drive the desalination here. So does it make sense to use this technology for agriculture? So I'll go through maybe some theory on why, for example, fractional salt removal might be an economically preferred way of desalinating. So this graph here is called the crop water salinity function. It describes the yield of crop as a function of how much water you apply to the crop. And here I present two curves, one for 1,000 microsiemens salinity, and one for slightly higher salinity, 1,500 microsiemens. And obviously, with the saltier water, it's not much saltier, you can see that you get reduced yield. So this is a grape crop. Now, the shape of this curve is different for every different crop. It's either shifted to the right, the left, up or down, but each different crop has a unique fingerprint or characteristic. It's to do with its, the way the root behaves in the soil and how it receives water in the presence of salt. So coming back to the question, does it make sense to use CDI for agriculture? Well, in the first instance, we asked the question, can we finance or fund a system desalination system from the increased revenue from growing or from having higher yield because you're using desalinated water? So in this case here, you apply 100 megalitres per hectare per year to this grape. If you pull out just 500 microsiemens, you get an extra $6,400 per hectare per year. Now, can you use that money to justify investing in desal technology? That's the question. And the answer is it depends. It depends on the crop, it depends on location factors, and a number of other things. So, addressing the issue of water scarcity in Australia, on the left here we have a map of groundwater and the salinity at different parts of the country. So it's highly variable. Because we like to treat brackish water, we would be targeting areas of the blue and the grey. On the right here is another figure which shows the suitability of grid-powered desalination of groundwater for agriculture. And it tends to centre, if you look, it has this dot pattern, and that coincides with population centres. So when you have grid power, the suitability of desalination for agriculture forms around population centres. But if you have solar, it's more likely to have a pattern that matches where these blue and grey areas are. So the next step for us was to do some detailed modelling of where the technology would be suitable. This is a framework that we use to model the economics of the technology. It has a number of components. It has a model of the technology and how it behaves. It factors in brine costs, irrigation costs, etc. It factors in the crop water salinity function I talked about, site characteristics, and bore modelling. And that is the equation there that describes all that. It has everything you can think of included. It's almost exhaustive in factoring in all the costs involved. And essentially it is the annual profit is equal to the yield multiplied by the area multiplied by the crop cost minus all the costs incurred, both ongoing and upfront capital costs. And we go through a case study now, just quickly at this location. And what you're looking at here is the end result of that modelling work. So you're looking at what's called isocontour profits, isoprofit contours, I think that's the term. These are regions of profit per hectare, and the absolute value numbers there describe how much profit you receive depending on what the on-crop salinity is and how much water you apply. So you typically pick a value where the profit is highest, which would be for citrus in the middle of that circle. For tomatoes, it would be somewhere in here. And it's different for each crop, and that's to do with how it responds to salinity. Each crop has a different characteristic. Similarly, for internal rate of return, we produce the figures, and it varies again for each crop. So we've analysed a number of crops and produced some data, again, on crop salinity and water applied. And the way you control where you want to be on this curve is by selecting the size of the system for this axis, and on this axis you just apply the water required to match the optimum value. So once you break down the various costs, you can see that a number of costs contribute to the total annualised cost, and this is a breakdown by percentage. I won't go into too much detail, but you can see the big ones are the crop ongoing costs, establishing the process to treat the brine, and the ongoing costs of the actual desalination process. They're significant. So how much time have I got? Over. Thank you. These are the conclusions. Thank you.
Thank you very much, Peter. Is there any questions from the audience? Yes, please.
Yes, my name is Jodine. I'm an agribusiness officer in the Agricultural Economics Division of FAO. And I would like to ask, what is your opinion of these being applied in small island developing states, say Marshall Islands or Tuvalu, that are going to face sea level rise? Thank you.
You will be limited again by the salinity. We don't want to, if you have seawater intrusion, it could potentially get up to say 10 or 15 grams per litre. We like to only operate below 4 grams per litre, but that doesn't mean we can't treat higher salinity. It means we need more electrode capacity. So what that then means is we need to reduce the costs of the electrodes. So the technology is in its infancy, and a lot of the work now is on automation of the technology. So I'm expecting, say, for example, in 10 years' time, the costs will be maybe 10 to 15% of what it is today. I mean, when you look at it, it's just that. So there's a lot of overheads in putting that into a box, and there's a lot of scope to reduce costs on that, and that will open up solving these problems, I think.
Another question?
Yeah.
Philip Davis. Can you achieve high recoveries? How does it work with recovery ratios? What's
yeah,
the limit?
Good question. We can actually dial in the recovery ratio that we want. There are some compromises there. You lose a bit of efficiency in the desalination. We operate it between 60 and 85%, depending on what we want to do with the process.
Okay. Yeah, thank you.
Is there any other questions? And so, yes.
I'll ask myself a question. How much does it cost to treat the brine? So that came up in Elizabeth's talk. Well, the number we use in our modelling is for a megalitre per day treatment of the brine, it's $1.5 million setup costs, and that's either by evaporation ponds or deep well injection. So 1.5 million for a megalitre to treat a megalitre per day. So that's the upfront cost, and that's the number we use in our modelling. Yeah, it's roughly the average of either evaporation ponds or deep well injection.
Okay, thank you very much. Peter, is there any questions from the audience?
Grubitsky, Land and Water FAO. I just had a follow-up question on your desorption process.
Yep.
What do you use for the desorption process? Are you introducing any other chemicals? And sorry, I guess that links to what you were just saying about the brine disposal and how you deal with that.
So when we operate the process, we run it on a cycle of 3 minutes of absorption and roughly 1 minute of desorption. So when we desorb, we reverse the voltage, and that pushes the salt off. And we capture a concentrated brine during that step. Does that answer your question?
Yes. Just to check, so there's no added chemicals at any point of your process?
Only we trigger, for example, a back pressure threshold where you have scale build up in the electrode, which is the same for electrodialysis, RO, etc. Then you need to do an acid clean or use sodium hydroxide to deal with it. But that is periodic, say every month. So, but during the routine cycles, no, we don't.
Okay, thank you very much, Peter. Is there any other questions to any of the panelists? Okay, so then I have a question for Elizabeth, maybe. Can you tell us a bit more on the impact of, okay, because we've been talking a lot about water desalination and so on, and can you tell us a bit more on the impact of solar desalination on the energy sector?
Yeah, this is actually a very interesting and exciting question, because also in Tunisia, in our project, we're starting to look at options and how to integrate, in fact, solar desalination plants also in the demand-side system, demand-side management of the electricity utility. So, in fact, as we go ahead with including more renewable energies that are fluctuating into the electricity grid, so we're talking about solar energy and wind energy mainly in Tunisia. We have like peaks in electricity production at certain points. And it would be interesting to see whether solar desalination plants that are intermittent can take up this electricity at points where there's high production peaks. So and I think that there could be an interesting role to play.
Actually, I just remembered. So in your best scenario, it was PV with electricity from the grid.
Yes.
And the question then is grid tariffs subsidized in Tunisia?
Yes. So this was with the best option. Yeah, that was the best option, and we had two cases like for the region, for the MENA region. So one was with an electricity tariff that is very highly subsidized. I think so. It was at the time the lowest tariff existing in the region, which was about 3.8 cents. And we had one scenario with the highest electricity price at the time. For the case of Tunisia, yes, electricity tariffs are subsidized. There are different kind of tariff groups. So a residential, a homeowner or a residential consumer would pay, depending also on in function of the consumption. So it's more subsidized for lower income households, and kind of gets more expensive for better income households. And then also there is still some subsidies also for non-residential consumers, but there's been a larger fade out during the last year. So they're still subsidizing it, but the subsidies are getting lower.
So did you by any chance looked at the scenario without any subsidies?
Excuse me?
Did you by any chance look at the scenario in which the price of grid electricity would be without any subsidies?
I think the scenario with the 17 cents is quite close to that, because I'm not sure like, whether there was a small subsidy included in the electricity tariff at the time, but it's getting very close to this scenario, yeah. So this was like one euro per cubic meter. Yeah. So it was still a very viable option in comparison to the others.
Thank you very much. I will now give the floor to the rapporteur to wrap up this session. Just when she will install herself, I would like to thank you all for attending this session. I think it was really interesting to see the different technologies, to have the overview, to have different ideas in Australia, in the Horn of Africa, and also in North Africa. And I really thank you deeply for attending this session. Thank you very much.
Thank you very much, Florent. And I think I will do a very quick wrap-up because we're nearly out of time. So this session, to me, has been extremely wide-ranging. We've started off really looking from the point of view of solar technologies, but I think there's, we've been talking about PV and what else? And I think the first real sort of lesson that came through to me was that where PV panels are dropping very fast in cost, what comes after isn't dropping as fast. And there are a whole range of technologies. I think we heard about some very, very exciting options. Of course, Charlie was the only one who actually wasn't talking about PV, but was talking about using heat and wind to drive the process, which was also very interesting. But it's another form of solar, isn't it?
Yes.
In arid regions.
Yes, sorry, I should have confessed. We do use solar PV to drive the reverse osmosis machine.
Okay.
So,
and then the wind...
Yes, I didn't explain.
The wind evaporation is coupled to that.
All the evaporation and all of that's done by the wind, but we have to pump water over the evaporator, which takes electricity, and we have a small reverse osmosis machine which needs power.
Okay, thank you. So, good, thanks. But to me, what was fascinating was to see the options in terms of membranes, in terms of the processes. So there's really been tremendous technological development in this area where we've been seeing the cost of membranes dropping steadily. But now we've got all sorts of other options, such as the CDI that we heard about, which I still have to look this up. The capacitative deionization, CDI. I think that's something that we're going to need to remember because that's a very exciting technology. I have to confess, I'm a chemical engineer with a PhD in chemical engineering, but that was quite some time ago. So I had to dig deep to try to remember the principles of the membrane filtration. I remember pretty well, but this sort of innovation was quite challenging. But I think that it's just so exciting to have these kinds of options for the future. Right. So linking these options into the electricity grid is one side of the story. And as Elizabeth pointed out to us, that this can really, for instance, the solar option is very good because it's using power at the peak times if you're bringing renewables into your grid. So that makes a lot of sense. But in fact, the session was also asking questions about water management. And on that side, we heard a number of options ranging from pumping groundwater to using seawater on the coast. I think a number of questions have not actually fully been answered here. And one of the things that was really worrying me during the discussion, and perhaps we'll have a chance to discuss during the tea break, was this almost assumption that coastal aquifers are becoming more and more saline. This is absolutely not necessary. I've been working in Cape Town with conjunctive use of surface water and groundwater. You drop a hydraulic curtain along the coast through injection wells. And you know, there are ways, particularly if you're using treated wastewater, you put injection wells along the coast and you can actually arrest that salinizing of the aquifer. And I'm afraid also the whole question of brine disposal, it does worry me because there is evidence in the Red Sea. Now this comes back to another sort of former hat that I used to wear in the Ramsar Convention on wetlands. There are fantastic ecosystems in the Red Sea, but there has actually been so much desalinization happening along the coast of the Red Sea that you are starting to see the impact on the marine ecosystems of the increasing salinity in the Red Sea. And of course, because there's not much flushing action going on there. So it's all very well to have evaporation ponds, to have, you know, deep well injection for the brine, but you know, yeah, I think this is something that we really need to take on board, and you know, not to sort of treat it as a sort of end of pipe issue that we can worry about if it becomes a problem. Because for me, as someone who's been working in the water sector, always advocating for solar desal, but my question has always been, you know, so what about the brine? I was absolutely thrilled to hear about the concept of the seawater greenhouses. This is a technology which, to me, ticks all the boxes in terms of carbon sequestration, bringing water back onto the land, creating areas of actually beyond simple delivery of water to the actual agricultural project, but it's got all sorts of spin-offs, as you showed us, with the possibility of the evaporation through the cardboard. I mean, this kind of out-of-the-box thinking, very, very innovative, I think is the sort of ideas that we're going to need to harvest and scale up, bring to scale very, very quickly if we're going to solve the challenges that people are facing in the years to come. So thank you very much to everybody involved in this session. It's just so exciting to hear about the innovative work that you're doing. Thank you to the audience for your questions, and this has been a very exciting contribution to this forum. Thank you.
Thank you very much. The session is now over. There is a coffee break in front of the David Lubin Library. So it's building A. Oh, thank you for the translators also.